Okay, so welcome everyone to the fifth session of our OpenMP programming. So in the previous session, we saw what is data race, why the data race happens, and we saw what is critical section. And then we saw multiple examples related to the critical section and data race, and we tried to remove the data race by placing the critical section in the multiple examples. So yeah, towards the end, we saw this thing, right? We saw how to do numerical integration using trapezoidal rule. And we saw basically we were seeing the serial program for writing, serial program for calculating the area under the curve using serial trapezoidal, using trapezoidal rule using serial program. So uh, there we stopped in the previous session. So we'll take up from here. Meanwhile, anyone who feel that anything was unclear, please unmute and ask. So I'm assuming that up till this point everything was clear. Yeah, if any questions, then let us take up. Else we can proceed with the today's session. So for the today's session, we'll be seeing how to parallelize this. That serial trapezoidal program that we saw, right? We'll parallelize that. We'll write the OpenMP parallel code for it. Then we'll see what is reduction, and yeah, towards the end we'll see parallel for and what is parallel for, and then we'll see its limitation. And if the time permits, we'll also look into barrier and atomics. But let us see how much time we have at the end. Yeah, so any questions up till now? Anyone? If there are any, then please feel free to post them. And yeah, one more thing regarding the feedback, let me quickly cover that also before I start today's session. Okay, so let me share that. Yeah, so regarding feedback, so far we received 18 responses, and feedback looks positive to me at least. So I hope that people are able to understand based on the responses that I've received. And yeah, the main thing that I was concerned about was the pace. So I think the pace is okay for many people. So I'll keep continuing with this pace and this way of teaching. And yeah, if there are anything that other things are, looks fine to me. So yeah, and comments also look good. And yeah, there were a few comments related to questions for interviews. So I'll only suggest that try learning the concept. So interviewer will ask only questions around the concepts that we are learning. So yeah, but yeah, we'll try to cover most of the concepts. So that's regarding the feedback. Now let us go back to our session. Let me share the slides back. Okay, so this was the place where we left last time, right? So we were seeing the serial trapezoidal rule. So quickly recapping what we saw. So we saw this, right? That we can calculate the area under the curve using this equation, right? And uh, we calculated this equation using uh, the summing up the area for each of the trapezium, and area of each of the trapezium was calculated as a plus b by 2 into h. So essentially, we summed up the area under all the area of all the trapeziums, and then we said that that is nothing but the area under the curve. And yeah, so that is the way we proceeded. Now let us try parallelizing this one. So okay, so let us move to the next slide. So what we'll essentially do here is that we'll let me share the whiteboard instead. So yeah, so what we'll do essentially here is that now we'll divide our trapeziums, n trapeziums that we have. So there are n trapeziums that we have, right? Sorry, we'll divide those n trapeziums among m threads for parallelization. And one thing to note here is that n, which is number of trapeziums, must be much greater than m, which is number of threads, and will give n by m trapeziums to each thread, right? So this is the way we'll divide the work for this for implementing the trapezoidal rule in parallel. So what will happen is that, let me draw a few more trapeziums here. Right. So what we'll do is we'll give, let's say, first two trapezium to thread 1, next two trapeziums to thread 2, another set, another next two set of trapeziums to thread 3. Should have taken different color actually, but yeah. Let me pick up the red one. So this is for thread 3 and this is for the thread 4. So I hope you're getting it. So here in this case, we have 8 trapeziums. There are 8 trapeziums, 1, 2, 3, 4, 5, 6, 7, and 8 trapeziums. And yeah, so we have 8 trapeziums and 4 threads. So we are giving 2 trapeziums to each thread. And that is how we are dividing the work here. So essentially, that is the idea. We'll divide all our trapeziums to the threads by using n by m. So each thread will get n by m number of threads. N by n number of trapeziums, and they'll calculate the area of each of these trapeziums. So thread 1 will calculate the area of trapeziums, let's say T1 and T2, trapezium T1 and T2, and they'll keep it as a, they'll keep that area, calculated value of the area in some local variable. And similarly, thread 2, it will calculate the area under the trapezium T3 and T4 and will store that area in some local variable and so on. And finally, after finding the area for each of the, when all the threads are done for computation of its own area, then they'll add all the values, right? So each of them will compute the its own area and own area of the trapeziums, and then later sum up the values and will that summed value will be the final area under the curve. So that is what we want, right? So that is the way we'll that's the way we'll parallelize this code. So quickly moving back to the slides. Yeah, so yeah, as I said, we'll divide n trapeziums among m threads. Each thread takes up n by m consecutive trapeziums. Yeah, so this is important. Each thread will take consecutive trapeziums only. So thread 0 will take trapezium number T1 and T2. Thread 1 will take T2 and T3, and so T3 and T4 and so on, as we saw, right? So let me quickly switch back. So as we saw here, right, each thread is taking consecutive trapezium. So this is thread 0 is taking this two, thread 1 is taking this two, and so on. So they are the consecutive set of trapeziums that they are taking. Now, yeah, so as I said, yeah, they are taking consecutive set of trapeziums, and n is much greater than m here. So number of trapeziums are much greater than number of threads, and n by m, n should be divisible by m. That is what we need, because otherwise we'll have some leftover trapeziums, right? So n should be divisible by m in this case. That will ensure in our code. And as we saw, our algorithm will be simple. What we'll do is each thread will find the sum of its own sum of area of its own set of trapezium, and at the end they'll add all this uh, area. So they'll hold that sum value in the local variable. So that is what is that local sum, and they'll add it to the global variable later, and that value inside the global variable is the final result, and the final area under the curve. So far so good, right? Any questions? Okay. So far so good. So um, that is fine. Now, in order to calculate the uh, area of each of its own set of trapeziums, each thread will need to have local A, local B, and local N, right? So if you remember from our previous discussion, let me quickly share that. Just let me go back. Yeah. So in case of serial code, if you remember, there was A was the lower limit, B was the upper limit, right? And since in case of serial, we only have a single thread, we don't have multiple threads. What we did was we found the area under the curve using A, B, and H. But here there are multiple threads, and each thread will calculate the sum of the area of its own set of trapeziums. So each thread need to know what is their local A, local B. So moving back to the example on the whiteboard, so thread one needs to know thread zero needs to know what is its local A and local B. So in case of thread zero, its local A will be A and local B will be this one, right? Okay. So this will be its local A and this will be its local B, right? LB, let's say. In case of thread one, this will be its local A. This point will be its local A and this will be its local B, and so on. For thread 2, this will be local A, this will be local B, and so on, right? So each thread need to know what is local A, local B, and local H. So how will we go about finding this? So I hope this is clear. Each thread will need to know its local A, local B, and local H, and we need to find those value for each thread. So how will we go about finding them? Any ideas or any suggestions? Please post them on the chat, or you can unmute and also answer them. So I'll wait here for a few seconds. Please try how to calculate local A, local B, and local H. Post that we'll discuss, and yeah, we'll also see the code. I hope that question is clear. If there is any doubt, then please do ask. Okay, any suggestions? How can we find these three things? Local A, local B, and local H. Okay, tell me one thing. How can we find local H? Any idea about that? Anyone?
So local edge should remain same across all threads. So I think that can be calculated before launching all the threads. So you are on mute.
Yeah, sorry, I was telling that that is correct. Local edge will be same for each thread. But how can we calculate that? Any formula or anything for that?
B minus A by N.
That will be global edge, right? So B minus A by N will be the yeah, sorry, local edge, not local edge. Yeah, sorry, I missed it. So let me correct it here. That is right. H will be same. Let me correct this one. So yeah, that is correct. Local H will be equals to H, and that will be equal to B minus A by N. We'll also need to calculate local N, right? The number of trapeziums that are allocated to each thread. So that we can calculate using the number of trapeziums by number of threads. So that is fine, right? Which will give the local n. So the number of trapeziums that each thread will work on. Now, how to calculate local A and local B? Any suggestions? I hope I was clear. Like H will be same, so H won't change for each trapezium because this is the H, right? So this won't change even after we allocate some number of trapeziums to each thread. And
He
local
A
n is
B
nothing but
B will be like the A for, let's say, for the first thread, then local N into the H.
okay. Can you post some post your answers in chat so that I can go through them? Okay, I'll wait for some more time. I think there are some responses. Let me check. Yeah, so Mitesh is saying local A equals to A plus thread ID into H, and local B is A plus trapeziums per thread into H. Okay, any other suggestions? How can we calculate local A and local B? So this will be needed for calculating the area under the curve, right? Because each thread needs to calculate area for its own set of trapeziums. E plus N. Okay. A plus N by H into H. Okay. Yeah, I think you people are close. Okay, let us look into it. So how can we calculate local A, right? Local A is nothing but A plus uh, yeah. So we'll start from A till where we'll go. We'll need to get the ID of thread, right? Thread ID actually. So not num threads. TID into H into local n, right? Is this one correct? Okay, let us verify this. So we start with A. So what will be the local A for thread 1? sorry, thread 0. So thread 0 has this two threads, right? Sorry, this two trapeziums, right? So it will start from here, local A plus TID. TID is 0 for this thread. So this entire thing will become 0. So this is correct, right? It will get this one as the local A. Now this will be the local A for thread T1. So it will start from here. Its TID is 1. 1 into H into local N. So local N is nothing but 2 because each thread will have 2 trapeziums. So it will move 2 heights ahead and it will start from here. So A plus this thing, right? So this is correct, right? Similarly for thread 2 and so on. So this is how we'll calculate our local A. I hope this is clear. And how we will calculate our local B? Local B is nothing but okay, this thing. Yeah, so local B is nothing but local A. Okay, I think there is some space issue here. Let me remove this. Yeah. So let me move to the new page itself. Local B is nothing but, okay, let me quickly check this one. Yeah. Yeah, so local B is nothing but local A plus local N into H, if I'm not wrong. So what is the formula for local B? And this is what is the formula for local A. So local A is clear, right? The way we saw this is the local A based on what we saw as per the example. A plus TID into H into local N. So TID will be different for different thread, and based on that, it will move on. Will keep on increasing in strides. So for thread 0, it will be nothing but A because TID is 0. For thread 1, it will be this one, this point here. Because TID is 1 and H into local N is nothing but H into 2. Similarly, for T2, it will be this point because TID is 2. So it will be nothing but A plus 2 into H into local N is again 2. So it is nothing but A into 4H. This thing. So it is nothing but this point, right? So I hope this is clear. So each thread will get its local A, and local B is as per this formula, which is nothing but local B is local A plus local N into H. So let us see this one for some threads so that we can also get some clarity here. So local A is nothing but as we saw, right, this local A. And what we are doing is we are adding local N into H. So local N is nothing but 2. That's value is fixed for this example at least. And into H. So it will be this thing, right? Okay, let me move to this one only. So for this particular example, it will be local A into 2 into H, which is correct, right? So if local A is this, let us say for thread 2, if local A is this thing, then what will be the local B? It should be, it should be whatever is local A plus 2 into H, right? So we are moving 2 steps ahead. So this would be local B for that thread 2, right? So I hope this is clear for at least for this case. And in general, this is the formula, local A and local B is this thing. Now, okay, so far so good. We got local A, local B, and local H is equals to H, which is the same, one and the same thing. And local N is nothing but total number of trapeziums by the number of threads that we have. So let us quickly move back to the slides. Yeah, so right, so we saw how we'll go about parallelizing this. We'll each thread will find its own area. I mean, some of the area of its own set of trapeziums, which are assigned to it, and we'll sum up all those areas and we'll find the total area under the curve. And we also understood how we can get local A, local B, and local N, as well as yeah. So local H is same as the H. So these things are clear. Now let us jump to the code so that we can understand how actually it works. So okay, let me switch to the code now. I'll share the code screen. Yeah, so I hope this is now visible to you. Sorry. So as we did in serial code, we have this A, B, final result, and thread count. All these are same. We are getting the thread count from command line, and what we are doing is we are keeping A as 1, B as pi, that is lower and upper limit as 1 and pi. N is total number of trapeziums, which we are keeping it as 32. Sorry, excuse me. So yeah, these all things are similar to the serial code so far. Now comes the interesting part. So now we are using this function called trapezoidal rule, and we are passing A, B, and N in final result. And all these things are also similar to the serial code, if you remember. Let me switch back. So in serial code also, we were doing this similar thing. We were passing A, B, N, and final result. Now, coming back to the parallel code, this is the function trapezoidal rule now. It takes the arguments N, A, B, and result as we did in serial code. But now the computation will be different, right? I mean, the entire set of trapeziums now need to be divided, and that will be done using the local A, local B, and local N. So if you see here, we have declared local B, local A, local B, local N, as we discussed. And now we also need this myRank and thread count, because we'll need what is the TID or thread ID of each thread and total number of threads, which is thread count. And we'll calculate them using our, we'll get them using our runtime routines. And yeah, this other variables are same as the serial code. We have H, total, and I. And H is calculated as P minus A by N, same as our serial code. Sorry. And N, A, and B are calculated as per we discussed. So N is nothing but local N is nothing but N by thread count, which is nothing but N by M. So in our case, M was the total number of threads. So N by thread count is nothing but local N, the number of trapeziums that each thread will have, which is nothing but local N. And local A, as we saw, right, it is nothing but A plus myRank into local N into H, right? So let us quickly switch to the whiteboard. Right, it is A into myRank, which is nothing but thread ID. Thread ID is nothing but the rank of that thread, right? So A plus thread ID into H into local N. So yeah, so switching back to the code, yeah, A into myRank into H into local N. So that is what is, that was what we saw in the our whiteboard calculation, right? So that is the local A. And what is local B? Local B is nothing but local A into local N into H. So local A plus local N into H, which is nothing but what is shown here. So any questions up till now? How we calculated local A, local B, local N? Anything related to that? If there are any questions, then please feel free to ask. And yeah, we can clarify that. Okay, so once we calculated, once we calculate this locally, local B, and local N, what we can do is we can calculate the total area under the, total area of the trapeziums that are assigned to that particular thread. And for that, we'll use the same formula, right? So the same way that we did in the serial code. In serial code, we use this, right? Right, f of a into f of a plus f of b by 2, and then we had this for loop, right? So the same thing we'll do here, but instead of a, b, and x, we'll use local a, local b, and local x. So local x will be calculated using local a here. So actually this should be local x, just for the sake of clarity. So yeah, same formula, but using local a, local b, and local x. So we'll get the area for the set of trapeziums that were assigned to that particular thread. And yeah, and yeah, later we'll also multiply it by h as we did in the serial code, right? At the end, we multiplied it by h. So this will give us the area for the set of trapeziums that were assigned to that particular thread, and that will store in total. Now, once that total is calculated, we'll add it to the result, and result is nothing but our global sum, in which we are adding all the local areas for the trapeziums that were calculated by each thread. So quickly moving back to the slides, if you remember here, we said that in the step 2, we'll add the local sum of area to the global variable, right? So this is what we are doing it here. So local sum, so this is local sum. Local sum of all trapeziums assigned to this thread, right? To the particular thread. So, okay, spelling is wrong. Yeah, but that's fine. So this is the local sum, and we'll add it to the global variable here in the result. Now, tell me two things. What are the local variables and the global variables in this code? And is there any issue? I mean, is there a data race within this code? Two questions. What are the local variables and the, I mean, local and, or let me put it in this way, what are the thread private variables and the shared variables? And is, and the second question is whether there is the, I mean, there is data race within this code or not. Please try to answer these two questions. I'll wait here for some time. And if there is any question related to this entire code, then also please ask them if there are any questions.
So the updation of result should be done in a critical section.
Yes, that is correct. And why is that the case? Why we need to update result in the critical section?
So because it's a shared variable.
Yes. So the question is, okay, so the result is the shared variable. That is correct, right? So what are the private variables here? Any other variable apart from result which is shared here in this code?
So within the function, no.
Yes, that is correct. So within the function, there is no variable which is shared apart from result, right? And rest of them are private variables. So even this int double a, I mean, sorry, int n double a double b, all these are private to each thread. And also this h, x, total, I, and so on, all these are also private because they are, I mean, they'll be they are declared for each, they'll be declared for each thread, and they'll all this will be stored in the stack of the each thread's I mean each thread's stack. So all these are private variable, as well as all these also. And coming to result, it's a shared variable. And as it is mentioned, so this thing, updating the result, this should be done in the critical section, right? Because result is the shared variable, and we are adding something to result, and each thread is doing independently, and there can be a potential data race here. So each thread is updating something inside the shared variable, and this can lead to data race. So what we need to do here is we need to do hash pragma omp critical. Okay, I think this is fine, right? So this is the data, right? For getting the correct result. So any questions up till now? Like, were you able to understand what we did so far? Like, why do we need this critical and how the entire calculation is happening? Any questions, please feel free to ask. So now we'll run this program. We'll see the output for serial as well as the parallel code, right? And we'll compare them to see whether it's giving the correct result or not. So let us do that. Right. So let us first run the serial code and see what is the output for this program. So let me do this GCC minus F OpenMP program serial. Right, it compiled, and now the output is area under the curve from 0 to pi is 0.19 something. So now let us see for the parallel version as well, right? So the output for the parallel code should match with the serial one. So let us do that also. So by the way, the serial code can compile even if we don't specify this F OpenMP, but yeah, it will give the same output. But for the parallel code, we need to specify the F OpenMP here. So program MP parallel, yeah. Okay, it is saying some issue with local X. Yeah, because we updated this one, right? So it should be now local X. Yeah, it compiled, and now let us run it with 4 threads, and it is giving the correct result, right? The same one as it gave for the serial code. So I hope this is clear. Just to do a quick recap, what we did was we divided the total set of trapeziums into, total set of trapeziums among n threads. Each thread will calculate the area for its own set of trapeziums. And for that, we'll need local A, local B, and local N. We saw how to calculate them. Then using that local A, local B, and local N, each thread was performing that area calculation using that same formula that we saw for the serial code. And at the end, they were adding that area into some global variable, which is result. And that result was, since it was a shared variable, and since the computation is happening in parallel, we need to ensure that we have a critical section. So yeah, we place that hash pragma MP critical for that. Okay, so assuming that this is clear, now let us switch back to our code screen. Yeah. So now let us look into the another way in which we can do this trapezoidal rule calculation. So we can do this thing also, right? Instead of, so okay, in the previous code, we were adding the result in some global variable, right? Instead of doing that, what we can do is we can return the result, right? We can return the local area that was calculated by each thread, and we can return that area. So instead of updating the local, shared variable here result, what we can do is we can basically calculate the total, which is the local area, and return that total, right? And within the main code, so rest all things are same, right? In the trapezoidal rule, the calculation will remain the same. Just that we need to calculate the local area and just return that. And within the main function, what we'll do is we'll sum that up. We'll sum the area that is written from each thread in the final result. So, and yeah, we'll do that thing in parallel. So we'll launch the n number of threads, and each thread will do this calculation of trapezoidal rule in parallel, and will sum up in the final result. So I hope this is clear. Any issue that you see with this code? Anything that you think is wrong with this code? Anyone?
So the final result variable will have a data race.
Yes. Yeah. So final result will have a data race here. Okay. I hope that you are getting it, because each thread is now calculating the trapezoidal rule in parallel and adding whatever the area it is getting into the final result in parallel. It will encounter a data race. So we can do this thing, right? Sorry. So to avoid this, we can do hash pragma OMP critical. But again, there is, by doing this, the data race will be removed. But again, there is one more problem. What is that problem? Anyone can point out that. So we have removed the data race. That is correct, right? From this by placing hash pragma OMP critical. But there is some another issue or some another problem with this code. Can anyone point that out?
So the performance boost won't be that much, and in some cases might be slower than the serial code.
Yes, so that is the problem here. So the performance might the performance might not be as much as we expect, right? Because everything is now serial. So each thread will execute this statement or essentially this function trapezoidal rule in serial manner, one after the another, because it is now it is placed inside the critical hash pragma of the critical. So this is the issue here. So to avoid this, what we can do is that, okay, let me comment this. Okay, let me keep it anyways. So to avoid this, what we can do is that instead of this piece of code, we can replace this entire thing with the one that I've written above here. So what essentially we can do is that we can launch a number of threads, and what we can do is we can declare a private variable for each thread, which is my result, and each thread will calculate the trapezoidal rule and will store the result in my result. And later, after this trapezoidal rule calculation is done for each thread in parallel, so please note that this calculation will be in parallel, right, for each thread, because each thread is now calling this trapezoidal rule independently and storing the result in my result. And after that, after the calculation and storing the result in my result variable, each thread will add its result in the final result variable. Yeah, for this addition part, adding their own, their local result or individual result into the final result, we can use this hash pragma OMP critical. So I hope this entire thing is clear. So there is some amount of parallelism here, right? We are not executing this entire thing in serial. This trapezoidal rule calculation will be done in parallel for each thread. Only the addition of the local result into the global variable final result is being done in a critical section, which is in serial fashion. So this entire thing, can be done in, OpenMP provides more better alternative for doing this entire thing. And that is nothing but the reduction clause that OpenMP provides. So reduction clause does the similar things under the hood. So what it does is when we specify the reduction clause, so let us come to this now. Let me comment this entire thing. Now let us look into how we can specify the reduction clause. Right. Okay. So let me remove this entire thing. So I can do this entire thing that we saw here, right? Using a simple clause, which is reduction clause. And within the reduction clause, what we need to provide is the operator and the variable, operator colon variable, which is final result here in this case. So by specifying this thing, what OpenMP does is that it will declare the private variable for each thread, as we did here, which is my result. So it will declare private variable for each thread, and the calculation or the computation of the function or any other computation will be done in parallel. Just that the addition of final result using this operator on this the variable that we have specified will happen in critical section. So that is what happens internally when we use this reduction and then specify operator in the variable. So let us quickly see the slides now. So yeah, so reduction is nothing but we are doing similar operation again and again on a particular set of elements. So here in this case, or the in case of example that we saw, the repeated operation that we were doing was calculation of the trapezoidal root. Sorry. So we are performing, if we are performing same set of operation over and over again on this set of elements, then we can use the reduction. And what OpenMP does is that it creates a temporary variable. So these temporary variables, are used by each thread for the calculation, and yeah, that reduction clause helps us in performing some form of recurring operations in parallel, which was that calculation of the trapezoidal rule. So yeah, that is what it is, and its syntax is nothing but as you can see here, its syntax is hash pragma OMP followed by directive. Directive can be parallel or anything else, and then the clause. So the so the clause part is nothing but reduction here, which is followed by operator and variable, operator colon variable. And operator can have this set, I mean, it can be any of these things. Sorry. So any questions on this slide? Anything that is unclear? So I hope you understood what the reduction is. So essentially, if we are doing same set of operations again and again, then we can use the reduction, and we need to specify the variable on which we are which we want to perform the reduction, as well as the operator. Yeah, so in summary, what OpenMP does is that it creates a private variable for each thread, which is nothing, yeah, it creates a private variable, which is nothing but a thread private variable for each thread. And it does that computation in parallel, and the critical section is followed, I mean, critical section is followed by that computation. So yeah, so the function call will happen first, or whatever computation is being specified will happen first, and then there will be critical section in which will add the result or perform that particular operation. So if operation is adding, then it will add. Otherwise, let's say it's multiplication, then it will multiply, and so on. And that will happen after that computation within the critical section. Yeah, so I hope this is clear. And one more important point to note here is that let us say in this case, right, in this code, the final result, no, not final result, but the thread private variable, right? So, okay, let me share the whiteboard, right? Yeah, so we are doing this thing, right? Let me put this out. We are doing this thing, right? So for each thread, let's say thread T1, we are declaring the private variable, and when we are doing trapezoidal rule, we are storing the result, right, in T1, T2, and so on. Now, these private variables are, uh, I mean, they are internally declared by OpenMP. But what's the initial value for this private variable? So the initial value that OpenMP gives to this set of private variables is nothing but the identity value for the operation that we define, right? So we define operation, uh, sorry. So while specifying the reduction clause, right, we define the operation, right? So if this operation is plus or let's say minus or anything, so based on the identity value for this operations operators, OpenMP defines the initial value. So for plus, it is 1, right? So identity value is 1 for plus. So if we define plus here, then it will initialize all these thread private variables to 1. Sorry, not 1, 0. For plus, it is 0. And for multiplication, it is 1, right? So based on the type of operation that we are performing, uh, it will initialize this thread private variable with the value accordingly, identity value of that operator. So yeah, that is what is specified here. So OpenMP initialize each thread's private variable to the identity value for the operator that we are specifying in the reduction clause. So I hope this is clear. Any questions up till now? Anything that is uh, anything that was unclear among, I mean, all these things that we discussed?
So can we define multiple reductions on the same thread batch?
Multiple reductions. So you're trying to say something like this. Okay, let me share the code screen so that I can. By multiple reduction, you mean to say reduction 1, reduction 2 here, like this? Something like this?
Yes, sir. So like same aggregation, but saved into different variables based on different operators.
Okay, let us try this then. Let us see if this one works. Right. I think this should give some error uh, as far as I have tried, but let us see if this works. Let me share my console. Okay, name of program is GCC. Use this. Right. So final result appears in more than one data clause, it is saying. So essentially what you can do is, okay, I'll tell you what we can do here. So I think there is no way in which you can use this for the multiple, I mean, if you are using it for multiple cases, I don't think it's possible, but let's say you have multiple variables in which you can, for which you want to define the reduction. So then what you can do is you can define variable 2 here also. So let's say that you wanted to perform minus operation on variable 2, then this is possible. So I think you can do this, provided that you have defined variable 2. So let us do this. Or okay. right? So you can define multiple variables here, but I think still you need to define a different negation operator here. So what you can do here is that you can define a separate reduction clause here, and you can do this thing, reduction minus and var2. You can do this thing. I think this will work, but the same set of variable you can't specify in two different reduction clause. So I think this should work. Let us try. Right, it compiled, and it will also give some valid output. So we haven't printed var2 here, but yeah, this one will work. So the point here is that we can define
the
multiple
console is
reduction.
not visible.
Okay. Yeah, so what I was trying to say is that this one compiled as well as ran without any error, this second one, where we define multiple reductions. But the point here that we want to derive is that for same variable, we can't specify the same variable in multiple reduction clause, but two different set of variables we can define within the different reduction clause. Or if you want to perform the same operation, let's say addition only on this variable 2, then you can also do this. You can specify here itself. If we are specifying we have the same operator, then we can do this thing also. And if you have different operator, then you can specify another reduction clause like this. I hope you are able to understand this one. Any questions?
Yeah. Thank you, sir.
Okay, let us, I think, yeah, we ran this one, right? What was the output actually? I need to check that also. Yeah, so it is giving 5.142, which is different than the previous one because I think our function itself is different. Let us check that quickly. Right, so yeah, function in this case is 1 plus sine x, while I think in previous case it was different. Yeah, it was sine x by 2 into x cube, sine x divided by 2 into x cube. So yeah, this will calculate the area under the curve correctly as we saw for the previous case. So using the same trapezoidal rule, it will calculate the area under the curve. And just for the this sake, I'll remove this thing just so that it can look cleaner. So yeah, so I hope you understood this one. So essentially reduction is nothing but this entire thing only. The OpenMP is doing this declaration of private variable, calculation of the computation of the function or whatever the computation is there in parallel, and at the end it is summing it up using the critical section. So this entire thing we can write it in a better way using this reduction. And yeah, we need to specify the operator and the variable that on which we are performing the reduction. So that is one. So this is what is the crux of this reduction. So I hope you understood this part. Okay, assuming that there are no further questions, so let us move ahead with our slides. Yeah, so now let us introduce a new directive, which is parallel for directive. Again, let us start with the example, and then we'll come to the slides to understand the things better. So let us go back to our program of the same trapezoidal rule, right? So this is our serial trapezoidal rule program, right? So we are doing nothing in parallel here. This is the serial code that we have. And this function trapezoidal rule is also serial in this case. Now, let us say that I want to parallelize this trapezoidal rule function in a different way. Then what I can do is, instead of parallelizing this part, launching this trapezoidal rule in parallel, not launching, but executing this trapezoidal rule in parallel using n threads and doing computation and then aggregating the results and so on. What I can simply do instead of that is that I can parallelize this loop, right? This is for loop. And how I can do this? I can use a parallel for construct. So let us introduce this parallel for construct. Right, so I can write this hash pragma OMP parallel for, and it will parallelize this entire loop, and it will do it on its own. We don't need to do anything like dividing the work or anything like that. So this will do things on its own, and we can also specify num threads here. And yeah, you can specify num threads as thread count. So what essentially will happen here is that this hash pragma OMP parallel for will divide the n iteration among thread count number of threads. So, okay, so let us say that our loop has n iterations in this case. So in this case, it's lesser than n actually, but let us say that it has n iterations and m threads. Then in general, what will happen is that n by m threads will be assigned to each, n by m iterations will be assigned to each thread. And that is how it will partition the work. It will divide the loop iterations. So the thing to notice here is that this parallel for construct is a work sharing construct, right? So okay, let me switch to the whiteboard now. So okay, so if you remember this parallel construct, right? What it was doing is that the whatever structured block of code which was following it, each thread was executing this, right? Each thread used to execute this structured block of code, and there was no work sharing. So this is the parallel clause. But what parallel for will do is after parallel for, that should be a for loop, right? For loop should be there, and only then it will work. So there should be a for loop. And the another point to note here is that this for loop, the iterations of for loop will be shared by the number of threads. Let's say you have specified m threads, then it will share the iteration or share the work of n iterations among m threads. So it is work sharing construct. So this parallel for is a work sharing construct, and yeah, and it should be followed by a for loop. That is what we know, right? And yeah, one more thing that we need to observe here is, okay, let me go back to the code. Yeah, what about this variable I, right? Will I be a shared variable or a private variable in this case? Because each thread is now executing different iterations, right? So thread 1 might be executing T0, T1. I mean, T0, T1 means the iteration 0, iteration 1. Thread 2 might be executing iteration 2, iteration 3, and so on. So shall this, what will be the status of this I variable I? Will it be a shared or a private for each thread? Any suggestions?
So it should be private for each thread.
Why? What will happen if it's a shared variable for each thread?
So we are incrementing I each time, right? So it doesn't make sense for it to be shared, because if it's shared, then like every thread would get a different, like wrong value of I if that's the case. So it has to be because it's a counter variable, right? So a counter will be like specific to each thread.
Yeah. So it should be a private variable because it is being incremented, as well as it might be getting updated somewhere. And if it's a shared, then it will again lead to that data race thing, right? So it has to be a private variable. So I is private for each thread. So yeah, the thing is clear, right? So I should be private. This I should be private, and this parallel for should be followed by a for loop. Yeah, and it's a work sharing construct, unlike that parallel directive, right? In parallel, each thread will execute the whatever is the structured block. Here the work will be shared. So n iterations will be shared among the number of threads that we are specifying. So any questions up till now? Anything odd that we can see in this code? Or everything looks fine with this code? Anything that you observe that is wrong with this code? Any questions?
So in this code, the total variable again is, I think, facing a data race.
Yes. So if you observe it correctly here, this total variable is again facing a data race, right? Because, okay, let me go to the whiteboard here to make it clear for others as well. So if you see here, right, we have some for loop and we are specifying I equals to 1. Okay, anyways, so there is some conditions, right? And then we are doing total equals to total plus something, right? Now, even if the iterations are divided among other threads, what can happen is that that thread T1, which let's say holds some iteration 0, 1, 2, let's say. Thread 2 is holding few other, sorry. Thread 2 is holding few other iterations, right? Let's say 3, 4, 5. It might happen that thread T1 in iteration 0 is updating total, as well as thread 2 in iteration 3 is updating total in parallel. And when these two threads are trying to update the same shared variable in parallel, what will happen is that there will be a data race. And one thing that you should observe here is that, let me go back to the program. This total is a shared variable because it is declared outside this parallel for. So whatever is declared outside this parallel for is the shared thing. So each thread will have, we will share the copy of this total variable. So again, this here it's a data race. So how we can remove this data race? Any suggestions? Or can you suggest multiple ways in which we can remove this data race?
So we can either put it in a critical section or we can pass in that reduction clause.
Yeah. So, okay. So I hope that this is clear, right? So here there is the data race, and there are two ways to remove this data race as you suggested here. So one is to use the critical section. So we can place this thing in critical section. But again, that will have some performance penalty. So best thing to do is that we can use reduction, because this function calculation will happen in parallel if we use reduction as we learned, right? So if we do reduction plus colon total, then it will give the better performance as compared to the writing the critical, putting this thing in critical section. Okay, any questions up till now? Anything that you feel like was unclear? Anything that you feel like is not understood properly or anything like that, then please do let me know. Okay, let us move ahead. And I also encourage you people to answer the questions that I'm asking, so that even I can get some level of confidence that yeah, you people are understanding what I'm trying to explain. Okay, so let us move back to the slides. Right, so as we saw, this parallel for directive has the syntax hash pragma OMP parallel for followed by clauses that we want to add, like reduction or thread count or anything like that. And a loop should be followed. Specifically, a for loop must be followed after this parallel directive. Sorry. And the loop variables, which are I, j, k, which are used for iterating over the loop, are private for each thread, unlike parallel directive. So in parallel directive, if we let's specify some variable I outside that parallel region, then it will be shared. in fact, here in this case also, let's say total variable was shared also in the case of the example that we saw. But yeah, the loop variables will be private for each thread. So that is one point. And the second thing is parallel for is a work sharing construct, as we understood, unlike parallel, where each thread will execute the structured block in parallel, structured block of code in parallel in case of hash pragma OMP parallel. But in case of hash pragma OMP parallel for, they'll divide the iterations. And n by thread count iterations will be assigned to each thread in general. And yeah, so the one another point that we can highlight here is that if you have multiple serial loops in your code, then you can incrementally parallelize this serial loop using this hash pragma OMP for. So okay, let me go back to the whiteboard again. So okay, there is something in chat. I need to check that. Yeah, so let us say that you have multiple for loops, right, in your code. For loop 1, for loop 2, and so on. Then you can parallelize this using hash pragma OMP for hash pragma OMP parallel for, and then after some time you can come back and parallelize the second one, and so on. Let's say third loop, you can come and parallelize after some more time, like, and yeah, so this is the way you can incrementally parallelize your code. So this is your entire code, and you can parallelize each and every for loop independently. So that is what is the incremental parallelization. And the thing to note here is that there will be a fork join structure here. So let us say that before for there was just one master thread that was running, then it will be forked. I mean, when this hash pragma OMP parallel for is encountered, it will fork multiple threads, right? And each thread will execute its set of iterations. Then once the for loop is finished, it will join back, and there will be one single master thread. And again, it will, when it encounters this hash pragma again, right, it will again fork multiple threads, and again, it will execute the set of iterations. Each thread will execute its set of own, I mean, it will execute its own set of iterations, and after the for loop, again, they'll merge. And yeah, then again, the serial code will continue, I mean, by the master thread. So this is master thread, and this is the team. So yeah, I hope this is clear. So it provides some way to incrementally parallelize the code. So this hash pragma OMP parallel for is used for incremental parallelization of the code, especially the for loops. So yeah, I hope this point is clear. So incremental parallelization using forking and joining of threads. Okay, any questions? Anything that is okay? I think there is some noise from someone. Let me quickly. Yeah, so now let us move ahead. So there are limitations to this parallel for directive. And the first limitation is that it should be followed by the for loop. So that thing we already saw. Second limitation is that it, I mean, we can only parallelize the for loop, and yeah, I think, yeah, this point is different. So for the for loop, I mean, it can only parallelize the for loop if the number of iterations are deterministic. So if it can determine the number of iteration prior, then only it will parallelize the for loop. Otherwise, it won't be able to parallelize those for loops. So let us look into this 2 points using the example. So first point is very clear, right? It can only parallelize the for loop. So if you want to parallelize the while loop or the do while loop, then it cannot parallelize. So writing hash pragma OMP parallel for followed by a while loop will not work. And the second point is it says that it will not parallelize the for loop if it cannot determine the number of iterations prior. So what does that mean? So I think let us look into this with the help of example. Yeah, so I think this one, yeah. So let us say that you have this simple code, right, in which yeah, let us remove all these things. We just need thread count, and yeah, let us define some integer I here, right? So we have this integer I and we have this simple for loop. I think AI was needed, sorry. Yeah, let us keep these things as it is. Let us say that you have this for loop, right? Now we have written this hash pragma MP parallel for followed by number of threads, and we have this for loop. Now, what the second point was saying that if it can't determine the number of iterations in a it can't determine the number of iterations prior, then it will not parallelize. But here it can determine, right, based on the value of I and the bounds and the incrementation. But let us say that you have something like this, right? Let us say that you have such kind of loop. So it is still a for loop, which is followed by hash pragma MP4. But here, the the number of iterations are not. I mean, it cannot determine the OpenMP cannot determine the number of iterations in I mean a prior during compilation. So it won't be able to parallelize. Right. So let us try and compile this one also so that we can understand. Let me share my console. Okay, so this one is right. So it compiled without using fopenmp flag. So if you see that serial code was correct, so there was no issue with that serial code. But when I put fopenmp flag in it, it will give the error, right? That expected iteration declaration or initialization before this semicolon. So essentially, it is trying to say that please initialize something so that it can determine the number of iterations prior. So essentially, the point is if OpenMP cannot parallelize this kind of loop because it will not be able to predict the number of iterations that this loop will have. And if it is not able to predict, then it will not parallelize. So, so that is what is the second point. It will not parallelize for loop if it cannot determine the number of iterations prior. And it will also not the so this third point says that it will also not parallelize the for loop if there is break or return statement in between. So let us try that one also. Let us try placing break or return statement and see what it gives. So now let us place this thing back. Okay, I equals to 0. Right? Yes. Let me add a break statement and see. So serial code should compile and it is compiling. Okay, I think I haven't shared. Yeah, so again, the serial code should compile and it is compiling fine. But as soon as I place the SAF OpenMP flag, it will say that error break statement used within OpenMP for loop. So it can't parallelize such loop as well, where there are break or return statements within the for loop. So I hope this point is also clear. The third point that we were seeing. Okay, and the fourth point is that yeah, so essentially it will only parallelize those loops which are in the canonical form or in the standard form. So when we say in standard form, okay, what we mean when we say in standard form, what essentially we mean to say is that it should follow this kind of structure, right? For I equals to something, some initialization, essentially, some initialization, followed by some bounds, right? I greater than something, less than something, or something like that, bounds, boundary condition, basically. Followed by some incrementation, increment or decrement or something like that of this loop variable. So if we have this kind of a loop, which is in canonical form, which is in standard form actually, so that is the case where OpenMP will be able to parallelize this for loop. Otherwise, it won't be able to. So essentially, it should be able to predict the number of iterations if it's in the standard form, and if it does that, then it will parallelize it. So that is what is our fourth point. So let us quickly switch back. And yeah, so basically this canonical or the standard form helps in calculation of the number of iterations in prior to the execution of that loop, so that it can parallelize the loop. Basically, it can divide the loop among the number of threads. So yeah, we saw this program, right, with essentially this points that we were trying to understand using this program, right? So we saw that. Now, okay, so all this is fine. Now let us move back to the code. So any other questions up till now? Anything that was unclear from this slide? Anything? If not, then let us go back to the code.
I have a question.
Yeah.
Sir, do the number of iterations being executed in the loop have to be determined at compile time or before the loop is being executed?
I think when you say before the loop is being executed, that is compile time only.
No, sir. So,
So,
for example, if we want to do the number of iterations on a variable that we are getting as, so for example, a user input, right? So that is something that is determined at versus if the programs that you have demonstrated so far have the end determined as a, I think, constant or it's the predefined constant, right?
Yeah.
So what is that?
Frankly speaking, I haven't tried that, but I think it should be the compile time only. So if you are not able, if OpenMP is not able to determine it during compilation, then I think it won't parallelize it. So talking about those programs, right, in which we were giving the some input during runtime and then trying to use that value within our program. So I haven't tried that, but okay, let us try that, right? It will be an interesting exercise for all of us. So I think it should not work, but yeah, let us check. So we have this thread count, right? So thread count here is getting its value during runtime. So let us try using this thread count here, right? And see whether it is able to parallelize it or not. My hunch is that it shouldn't, but yeah, let us see. Let me share the console. Serial, it compiles. Parallel, it gives error. Yeah, it is because of break. Let me remove that break. Okay, let me remove the break. Let us see if it runs. So basically what we are trying to do is run the number of iterations based on the thread count. Let us see if it is able to do. It is right. It is able to do. So yeah, from this we can conclude that it is also able to do it during runtime as well, right? So if it is able to determine the bounds during runtime, then also it will parallelize it, right? So yeah, nice question. Thanks for asking this one. Even I was unaware about this. Thanks.
Okay, thank you, sir.
Yeah, so let us go back to the slides. Yeah, so please feel free to ask the questions, because sometimes the few of the things I even want to be aware about it, and we can learn together if we we can learn together if we can get some good observations or questions around the things that we're learning. So yeah, let us switch back to the code. Let us do one more coding exercise. I think I have a couple of them. Yeah. So let us look into this code now. So this is very simple code in which we are making two function calls. I think we are towards the end of the time, but yeah, let us look into the first function call, which is to work one. So here, what we are doing is we are declaring the integer variable I. We are declaring another integer, integer sum, which is initialized to 0. And then we have this for loop, which is initializing I from, array I, which is the ith entry of the array with I value. So a of 0 will be initialized to 0, a of 1 will be initialized to 1, and so on. So yeah, and then we have this for loop in which we are incrementing a of I to a of I plus 1, and we are then summing, we are adding a of I plus 1, a of I plus 1 to this sum, and then we are printing. So assuming that we don't have this, right, this thing, then what should be the output of sum? Quickly, anyone can predict that? Let us say that we don't have anything in parallel. We don't have this hash pragma, right? Parallel. Then what should be the output for this function? And considering the function we have, what should be the value of sum? Quickly, anyone can answer that? Or can type on the chat, like anyways is okay.
So it should be 50.
It should be 50. I think it should not be 50. Okay, anyone else who have different opinion than what is suggested? Okay, so essentially in the case of serial, so for serial case, I'll answer it, but after that we can look for the parallel case. So in serial case, it is doing nothing else but adding the numbers from 0 to 9, because let us say that in 0th iteration, a of 0 is updated, but we are adding a of 1 to the sum, which is nothing but 1, because a of I is initialized to I. So in 0th iteration, it will add 1 to the sum. In second iteration, in the first iteration, considering the iteration starts from 0. In first iteration, it will add 2. In second iteration, it will add 3, and so on. And it will go till, I think, 8. And during 8th iteration, it will add 9, because we are adding a of I plus 1. So it should give sum from 0 to 9, which is 45. Let us quickly verify that also. So let me share this thing. Right. The program is I think, yeah, this one. Right, it is giving 45. So there are two 45s because there are two function calls. But yeah, essentially the serial code is clear, right? Now let us move to the parallelization part quickly. I'll take 1 or 2 more minutes. What will happen if I do this, right? Hash pragma MP parallel for, and reduction also is added for the sum variable, because sum is the shared one, right? AI is also the shared, array is also shared, but we are not, each thread is, in this case, will not, it will update the ith entry only. So no issues with that, but sum is shared and it will be updated by multiple threads among different iterations. So some should be within the reduction. Now, anything odd that you feel for this code? Or maybe I'll keep this for the next session, but please think about what can be the issue with this code, and we'll continue from here. But yeah, please think about it. What is wrong with this code? Will it give the correct result? What will happen with this code? So essentially, from correct result, I mean it should match the result of the serial code. So for serial code, it was 45, right? So it should give 45 as the result. Same with the serial code. Yeah, so I'll stop here because since we are, I mean, above our uh, time limit, so I'll stop here. But yeah, please think about this, and I'll wait here for a few minutes for any questions that you people have. Also, if any suggestions that you would like to give. Okay, Kuldeep is saying 45 out. Okay. For serial case, that is correct. 45 should be the output. But please think about this case as well, where we are parallelizing it. And what will be the output, or is there any issue or anything like that? Okay, I'll stop here and yeah, wait for questions. Okay, so just one general question to everyone. You're able to understand the things that were explained, right? For the trapezoidal rule and all those things that we studied today, right? Can you let me know in the chat that you people were able to get the concepts that I was trying to teach in trapezoidal rule, how the calculation were happening and so on. Okay, I can see few yes. If there, I mean, if there is anyone who was not able to understand what I was trying to convey, then do let me know. I can connect with you so that we can have some clarity over there. And yeah, I'll continue with this pace because yeah, majority people are saying that this is the convenient speed for them. So yeah. Okay, cool. They be saying, sir, my question, how to cover past topics. Okay, can you clarify what do you mean when you say, sir, my question, how to cover past topics? So you can go through recordings if you want, like for past topics, if you want to get some. Yeah, if for the past sessions, if you want to get some idea, then you can go through the recordings. And if there are any questions, then you can post on the group. Yeah, do let me know if you have any questions after going through the recordings. Yeah, stop sharing. Okay, if there are no questions, then let us call it a day and see you tomorrow at 5 p.m. Bye.